No. They are like the people.
Ach so.
They only react with itself.
Ach so. So this would be kind of like when you hear the bang. Yeah, basically.
That's right.
Okay, bang. That was a misconception cleared away by Ralf. Okay, so when is something really ready to handle hydrogen? When can it get the stamp H2 ready? And what are some of the misconceptions around this topic? That's what we're going to be looking at today at Hyfindr Tech Talk. Welcome. My name is Steven, and I have a guest here who's an expert in failure analysis of all types, especially also hydrogen cases. So he knows when the stuff breaks, so he knows how to make it safe. And he works for a company that makes things safe. It's called Dekra, and they have been doing that for the last 100 years. They have a lot of expertise around this whole hydrogen topic, and Ralf himself has a PhD in material science. Welcome, Ralf Malke.
Hello, welcome.
Great to have you, Ralf. So when is something H2 ready?
Oh, H2 ready means I can use a component or material for the use under hydrogen conditions, under hydrogen atmosphere.
Okay, so anything that's under hydrogen conditions. So where would one normally find this?
At the moment, we find it, for example, in gas burners in households.
Yes.
But in the future, we will find it in a lot of fields.
Yeah.
Maybe for the transport, maybe for power plants, maybe for electrolyzers, and we have to handle these hydrogens,
yes.
And we have to transport the hydrogen from its source to all the areas.
Okay, so and I see you have a bit of a slide to even show that. So it's in the household, which you've mentioned, yeah.
Yeah, we have here in the households.
Yeah.
That's normal gas burners.
Yes.
We have the power plants for gas turbines.
Yes.
And electrolyzers, where we produce in the fuel cells, where we produce from hydrogen the electricity, but also we have the storages, and then we have also the mobility field.
Yeah.
Either if there is a fuel cell in the car, or there is the gas, which and the engine runs with the hydrogen gas.
Yes, the ICE engine. And of course your industrial applications, commercial applications, and maybe aviation coming at some point.
Yeah, but there are a lot of questions for the aviation.
Okay, then you have the H2 air this year.
That's right.
Okay, cool. Now, Ralf, let's go right in. So yes, it's in all these areas, but can you tell us a little bit about this thing? So when hydrogen is around material, what exactly happens, and why do we need to, take care?
Okay, then let's talk. Where how comes hydrogen to the material?
Yes,
we have on the one hand we have what we see on the further slide.
Yeah.
We see the pressure. We see a storage. We have tanks. We have pipelines and so on. There we have the gas, and the gas comes directly to the material.
Okay.
Also in even corrosion process, or in the most corrosion processes, we have we produce hydrogen. That's often a thing.
So as it's rusting, it's producing hydrogen.
Yeah, there's the chemical reaction.
Right.
We have water,
yes,
and you have the chemical reaction with the material surface.
Yes.
Then you produce hydrogen, which also can come into the material.
All right. Okay. Interesting.
Yeah, and then we have a lot of further processes like the steel making itself.
Yes.
Like welding. Like heat treatments.
Yes.
If we want to remove, for example, color from the surface, we use a pickling process.
Okay.
And also in the galvanizing process,
right.
If you get hydrogen, because there you have to, before you galvanize a surface, you have to clean it.
Yes.
And you use therefore you use fluid to remove all the rust, all the colors and so on from the surface.
Okay, so this is essentially where material already gets in contact.
Yeah.
And please take us a little bit deeper as to what happens to the material.
Yes. What we are talking about, or in former times, we are mostly talking about hydrogen embrittlement coming from processes what I described before.
Yeah.
But now, if we are in a pipeline, for example, we have hydrogen molecules, and that's totally different to the hydrogen atoms, because an embrittlement needs first that we have the atoms.
All right.
If we have hydrogen molecules, they are too large that they can't into the material.
Okay.
Therefore, we need a process here on the metal surface.
So on this chart we see this is essentially the material side, and this is the gas on this side. So hydrogen gas.
Yes, that's a hydrogen gas, maybe under pressure.
Yeah.
And here we have the surface, a surface layer, maybe an oxide.
Okay.
And here we have the material.
Yes.
And what you see here is we have first to remove the oxide, because only when we remove the oxide, then the hydrogen atoms would come into the material.
All right. So this is, if this were the inside lining of, say, a pipeline or a tank or anything else, and there were some let's say protective layer here.
No, it's not a protective. It's maybe also a layer which is coming from the material itself.
All right.
Yeah.
Okay. So this essentially, when this layer is already, let's say, broken, then it's already more susceptible.
If we have some gaps here, then the hydrogen atoms, which we were here, we see here the division of the molecules to the atoms.
Yes.
And then the hydrogen atoms, we know hydrogen atoms are the first atom in the periodic system. It's very, very small.
Yes.
And these small atoms can diffuse into the material.
Okay. So what you said earlier, so in the gas, it's normally molecular form, so H2.
H2, yeah.
But the ones we should be more afraid of is when they are, let's say, H only.
So it's only the atom.
Yes. Okay. Only, and that we would see, for example, with the rusting, with the corrosion that you mentioned.
If you have a corrosion process, then you can produce atoms, and they will come directly into the material.
Okay, so when they get into the material, so this is it's just like a grid kind of.
It's like a lattice. Like a lattice.
Okay, this is a metallic structure, so it's lattice. That's how the molecules are arranged.
And if the hydrogen atoms are in the lattice, I think we should switch to the.
This.
Yeah, here we have we see here also the grid or the lattice of the metal.
Yes.
And inside we have different possibilities for the hydrogen that they can stay here in the lattice.
Yes.
If there is a failure in the lattice, then we have a gap, and then the atoms comes into the gap, and what do the atoms want? They want to come together.
Yeah.
And then they are building forming the molecules.
Yes.
And that's the problem, because the molecules are much larger in the volume, and this leads to internal stresses, which were initiated in the lattice.
All right.
And what we also have, if we have some oxides in the material, or some atoms which are not normally in the lattice of a metal, then these are also traps. We call them traps.
Okay.
And the hydrogen comes to these traps and also combine together to the molecules. And then we have also the increasing of the internal stresses, and that's the problem.
Okay, so the atoms get into this structure, maneuver themselves through here, can react with other material. Do they react with the actual metal, or
no? They're only They are like the people. They only react with itself.
So they're looking for other
hydrogen atoms, and then they combine together to H2.
Okay,
and H2 it's much volume. Then we get internal stresses in the material.
Okay, so formerly this whole structure was relaxed. Now it's got all these bigger molecules, and it's all getting all stressed in there. Okay, so there's more people moving into the flat. Okay, and what do we see here? Is this?
Yes, if we have a failure in the lattice, there is a failure, or also more energy in the lattice.
Yes.
The physical energy in the lattice, and more energy means
what
also.
What do you mean by failure in the lattice?
If here, and you say these are atoms from the metal,
Yeah.
maybe ferro,
Yeah.
then they are not really aligned here very straight.
Okay.
If there are, here you see here there is a gap, or they are a little bit moved.
Also, or some impurity, maybe?
Yeah, impurity. Yeah.
Yeah.
Then you have then we have here a gap, or we have
Okay.
more energy.
So they should be all in line, yeah. But sometimes we have these
Yeah.
exceptions, and that will be a failure, and that makes it also more conducive for a
Yes,
error to
that's
happen.
right.
And what do we see here? Why are these not?
This is all the same here, but what happens here? Yeah, we have here dislocations and so on, grain boundaries. You see, metal is not built up like lines of atoms.
Yeah.
We have different areas,
Yes.
which have, there are the lines in this direction,
All right.
and the other side that is in this direction.
Okay,
And
okay.
the connection between these areas, we
Yes.
call them grain boundaries.
Okay.
And the grain boundaries are also a good street for the atoms
okay.
to move to some traps, to move to some failures in the lattice.
Okay. So now we're talking about metallic materials, obviously. Are there things that you can do to make it, better or not better?
Yeah, we can
To handle hydrogen.
Yeah, we can use different lattices for the material, because the lattice, not each lattice reacts in the same way with the hydrogen.
Right.
And we see it on this slide. Normally we have a ferrite.
Yes.
It's a ferrite structure, and here you see we have large distances between the molecules.
Yes.
And there we have, then we can see that hydrogen can move on the gaps between these molecules.
Yeah.
So, but this is a normal ferrite is not so critical, as we have the martensite. The martensite structure is when we harden the material, or and we want to get very high strength in the material, then we took this ferrite lattice,
Yeah.
and we stretch it.
Okay. Okay.
And therefore, yeah.
So now you're talking about, so essentially we're talking about metal, steel kind of handling here. So this would be normal, and this is now when you're trying to harden it. Then that changes the structure.
Yes.
Yeah.
Let's change the structure. You stretch it.
Yes.
You get internal stresses.
Yes.
And that's these internal stresses are you want to have.
You want to have.
But but if there are, in addition, there comes hydrogen, then it becomes critical.
So when do you want to have that?
If you want to have a high strength material,
then you strain it a bit.
Yeah, you hardened it, you tempered it,
okay,
and you get high strength with ductility.
Yeah.
But if you take this martensite, which is here, you see here the distance becomes larger than that. So, and then and if there comes in addition the hydrogen molecule, you get more internal stresses.
Right.
And then you get the embrittlement of the material.
Okay, that's when the hydrogen comes in there. Okay. So martensite we've seen. What is this austenite?
The austenite is the structure what we have in the corrosion resistance material.
Right.
And therefore, and here the austenite, the lattice is very close together, all the atoms. And therefore it's very hard for the hydrogen to come inside these.
That's how it becomes corrosion resistant.
The corrosion resistance. The corrosion
I thought I was getting it now.
The corrosion resistance is normally only caused by the passive layer on the surface.
So. Okay, so it's not even about the metallic.
No, it's no. The most people mean that the corrosion resistance is inside the material. A little bit, but the most thing what makes the material corrosion resistant is the oxide layer of the chromium, which is on the outside of the surface.
Okay, bang! There was a misconception cleared away by Ralf. Okay, so only the very outside of the chromium.
And if you damage these layer, then you can also that
Okay.
you are
So that's taking us back to this.
Yes.
Yeah. Okay. So all right. Okay. Okay. Cool. So right. So now when you say we can harden material and you can have all these different kinds of treatments.
Yeah.
I know that you at Dekra, you test this, you check for this, right?
Yes, we check this, and here we have some comparison between this is an only hardened material.
Okay.
Here in the top. In the bottom, we have a tempered.
Okay. So just to see what, sorry to interrupt you, but just to see what we're saying here. So this is a
tensile test.
Oh, this is a tensile test. So basically you're trying to
we have
pull it.
we have a sample and we clamped it. And we pull it together.
This is the one. Yeah?
This
Can you
is
show us how this works?
Yeah, this is maybe such a sample, tensile test sample.
Yeah.
They were clamped here.
Over here.
They were clamped here with the threads.
Yes.
And then we
so this was together like this.
This was first together,
and then
we get the force on the sample, and we pull it out to pull it
apart. Okay. So essentially, what we are seeing, I think we can see that here.
Yeah. Here you have also the reduction of the diameter.
Yeah.
This is the plasticity.
But this happens. So when you put it in, it's the same diameter. The reduction of diameter only happens through the pull, right?
Yeah, that's
okay. Right. Okay. So what we see here is you put it in, and this is the amount that it stretches.
Yeah,
right?
we increase the force.
You increase the force.
Yeah, and that's the increasing of the force.
Yeah.
And then we have here the boundary of the elasticity.
And
then then the material plastifies here, and this point is the strength of the material.
Okay, so this is the elastic portion where, as you pull it, it gets a little bit longer, but if you leave it, it would come back.
It would come back to the zero.
Yeah.
And if you are in this area, then it would also come back, but you have first plasticity.
Okay, so deformation, so it won't come back to zero.
Yeah.
Okay, cool. So you keep pulling, and then what happens?
And then we increase the force, and then it will crack here. But when we
so this line is when it breaks, it's broken.
Yeah. This line is the broken. Yeah.
So this is a tempered steel, and this is
only hardened steel.
Only hardened steel.
Hardened steel.
So we see the same force being applied, the same elasticity more or less, and then these are the break points. So this would be broken here. So this would be kind of like when you hear the bang. Yeah, basically.
That's right.
These are the bang points.
Those are the bang points.
Okay.
But what we see here is if we aged some samples in hydrogen for 50 days, probably, then the broken point is here. And when they are not aged, then the broken point is here. This means during the 50 days, the hydrogen went into the material, and we get an internal embrittlement.
Yes.
And these internal embrittlement, internal stresses, reduces the ductility of the material, and therefore we get early breakage. We have nearly the same height of the tensile test, but we get an early breakage and less plasticity. And if we only harden it, then it's very critical, because then due to the internal stresses of the hardening process and together with the internal stresses of the hydrogen, then we have a very early breakage of the sample.
Okay, so what you're saying is this green line here, I don't know if that's visible, and this one, this is essentially showing a sample that has been aged in hydrogen for a while.
Yes.
Whereas the other lines are samples that were not exposed to hydrogen. So just very clearly shows here that if it has been in hydrogen for 50 days, that metal will not hold as much.
The plasticity of the metal was reduced.
Okay. So so for hardened steel, there is also an effect. The plasticity. What is the effect here?
Here is also the plasticity. It's the same. The x-axis is the same.
Yes.
hardened steel has a very high strength.
Yes.
You see it here. It's
Yes.
it's a lot of strength.
Yes.
But we won't come to, if there is an aging process in hydrogen, we won't come to the high stress, because we have so much internal stresses.
Yeah.
So that the breakage comes very early.
Okay, and that's so. What has happened there? Tell us. This is now the hydrogen has gone into the material and has kind of weakened it. Like
we had the recombination of the atoms to the molecules.
Yes.
And due to these volume increasing, we have the internal stresses.
Yeah. All right.
Yeah.
Okay. So, and is that now the legendary embrittlement?
That's the legendary embrittlement.
Okay.
Very, very simple.
Can we just? I just want to go back just one video because this is so important. So show us embrittlement here. Can we see that on this?
No, that's the embrittlement is here when we coming back to the molecules.
Yes.
Then we have the embrittlement. Each molecule in the hydrogen in the lattice will increase or will decrease the plasticity.
Yes.
And because it means molecule volume, larger volume, we have an internal stresses.
So the hydrogen having gone into the material, now causing internal stresses, reducing the plasticity, that's embrittlement.
That's embrittlement.
Right. Can we see embrittlement? I mean, you brought some samples here. Can we see them?
These are choppy. These are choppy notched impact test samples.
Yeah.
And we see here, this is a very flat surface.
Okay, this over here.
Okay. Without any large plasticity around the edges.
Yeah.
Here we have the sample.
Okay.
We have a large plasticity.
Okay, so that means here I can see the kind of went up and okay, that is.
Here it's even flat.
Okay, okay.
And these here we have the plasticity. Here we have no plasticity.
Okay, so no plasticity means
and here we have what we also see here is there is for the engineering. You see, I want first to have a leak and then the fracture.
Okay.
Because when you see the leak, you know that something going wrong.
Yeah.
If we have first the fracture, you can do nothing.
You can't do anything.
That's leakage for breakage.
Okay. So of these two, am I correct in saying that this is the one that had embrittlement?
That's embrittlement.
Exactly. So here you would have the breakage before the leakage. Here at least there will be some leakage before the breakage. Okay. So that's perfectly taking us into the next topic, because I know you said earlier that part of being ready for hydrogen, H2 ready, is that it's going to be leak tight.
Yes,
right?
That's right.
Right. So no leakage.
Yeah.
So tell us, to be honest, someone said to me once that there is nothing as 100% leak tightness. Nothing is ever completely tight. But then again, we talk about being leak tight.
Yes, but what is tightness? Tightness is we in the engineering we have to define the leakage rate to say, okay, someone is tight. If we said we have a very low leakage rate, then we can say it's tight. If we have a high leakage rate, then it could be also said for someone it's okay.
Yeah.
If you have water, and it's no drops is on your pipe, and you can say it's leak. It's all tight.
Okay, but wait. For Dekra, when is it tight?
Well, let me explain here something. If we have here 10 up to -3, and here we see some bubbles on. It's one bubble per second.
Okay.
If you have 10 up to -11, then it means we have loss of gas. Here the 1 cubic centimeter in 3,000 years.
Okay, so these are different leakage rates.
These are different leakage rates.
And this is how big the opening is. Is this correct? Or no? Or what? I don't know. Diameter of the leak.
Yeah, that's the diameter of the leak. Yeah.
And this is like what it will.
The amount of the gas which comes out of the leak.
Okay, so here in this 10 minus to the power -3. you get one bubble per second.
Yeah.
So bloop, bloop kind of
Yeah.
thing. Yeah. Here 10 minus 6, you would get one
1 cubic centimeter.
cubic centimeter. That is
in
more than a
12,
bubble. That's
yeah.
big. Yeah. In 12 days.
But in 12 days, yes.
In 12 days.
Yes.
Okay. So 1 cubic centimeter. So one small bubble is 1 cubic millimeter.
Yeah.
Okay, right. Okay, so this would be 1,000 cubic millimeter. Yeah, more or less. Isn't it? I'm
Yeah,
getting
it's
my math right.
10,
Yeah, I hope so.
yeah, it's 1,000. Yeah.
Yes, 1,000 cubic millimeters in 12 days. Okay, so that's a couple of bubbles.
Yeah.
Yeah. And here we would have 10 to the power minus 8. That would be 3 cubic centimeter gases in 1 year. So these are definitions. So you get like 3,000 bubbles in a year.
Yeah. But it's
That's like 10
but
bubbles
you have
a day.
do you have a very sharp view?
Yeah, that's like 10 bubbles a day.
Yeah, that's the problem. And therefore, we said if you have a leakage rate in a pipeline,
Yeah.
and you have only one bubble per day, or
Yeah.
then it's you have to say it's tight,
Yeah.
because there is no absolute tightness in the system.
So your typical pipeline, what would it have?
I think the typical pipeline. I think we will go to this one 10
to the power minus 8.
Yeah, it should be,
Because
because
10 to the power minus 11. Okay.
that's not that, because if you want a high tightness,
Yeah.
that also increases the cost significantly.
Well, okay. I'm sure some of the guys, some of the business guys watching here are already calculating, like, how much hydrogen per year cost then? How much does the pipeline increase per cost? And then you say, okay, how much, where's like my sweet spot?
Yeah, but it's also, you have it's dependent on the pressure.
Yes.
Yeah, and the next thing is, if you have natural gas,
Yeah.
you have a leakage rate.
Yeah.
Then it's not so critical than if you have maybe hydrogen, because if you have hydrogen and oxygen and maybe electricity, which like a sparkle, then there we get the explosion, the danger of explosion.
I mean, then again, when it's just one bubble or bubblito, as the Spanish people would say, it might be small.
If you have one bubble, then it's not the problem.
Yeah, because I mean, see, look at 10 to the power minus 11. That's 1 cubic centimeter. So that's 1,000 bubbles in 3,000 years. Yo, so what's that? One bubble every 3 years. Yeah. Okay.
Yeah.
Okay. That is. And I mean, if we're talking about a bubble, that is really not a dangerous.
No, because you have also there are standards which define the critical mass or the critical volume of gas, so that something could explode.
Okay.
And when we do in engineering, we want to get below these critical rates.
Yes.
And then it should be no problem.
Okay. So now, just coming back to my question of, for a typical pipeline or like a typical hydrogen application, what kind of leak tightness are you looking for? If I want to build a pipeline under the Dekra headquarters, which one should I go for?
I think normally we would calculate with such 10 up to -6.
Yeah, okay.
In this range.
In this range. I mean, there is also a little bit of hydrogen in the air already anyway. Yeah, so probably that wouldn't even be it's probably also hard to detect in that sense. Yeah. So what are some of the things that we do to the material to make it leak tight?
Well, there are different concepts. Maybe we can see here the tank.
Yeah.
Tank has two. There are two different things. The one thing is that it should be tightened. You want to storage something. And the other thing is it should be stiff enough. So that we can, because here we have the pressure of maybe 100 bar. It should resist the pressure of the. Therefore, we have here a Titan inliner. It could be made of metal or here of polymer, and we have the carbon fibers who are responsible for the stiffness.
Okay. Well, okay, I have to say here that there's obviously different kinds of containers or tanks that you can use for hydrogen. There's, I think this is what you have with type 4 here, right? Yeah.
Yes.
So with a different liner inside. Yeah. And so a tank that has all this, which you've shown here, in what category would that typically go? Also somewhere here.
Here also we want to get in this range.
In this range
of the
even on the 700 bar kind of, yeah. So you have 700 bar and you have that kind of leak.
Yeah, but the 700 bars, there are at the moment we are talking for pipelines. We are talking about 100 bars.
Okay.
Yeah. In the storage or also in the fuel stations, the pressure was raised.
Yeah.
And therefore we get higher pressures, but also we get smaller diameters of the pipes.
Okay. So that makes it easier for the pipe, basically.
For the pipe, and therefore also for the volumes. And that's why we can rise up the pressure.
Okay. So I mean, we have talked in this studio about different types of like connections and also like gluing them and also detection. I think it's always interesting to look at how the pipes are actually connected, and then I know you have something to say about that as well.
Yes, we can see connection, which is only there is no seal inside. The tightness is only comes here only from the moment where we put or we press both parts here together.
Okay.
And these are very smooth surfaces, and due to the pressure here between with this connection, we can here have a very high tightness.
Yes.
Here it's only maybe a problem that we have here to get these geometry.
Okay.
Yeah? You have to deform the pipe, and what we learned before, deformation means internal stresses.
Okay, so that means that here you have some of those internal stresses happening already.
Yeah,
and that makes the material a little bit more susceptible. You know, like, all right. Okay, interesting. And what I personally found interesting, this whole thing of not using a seal. So you literally just put metal to metal, putting them together, and then hope to have it.
Yeah.
Is it really more tight to have metal on metal than to have a sealing material in between?
Yes, because the sealing material is a second material, and this should also withstand then the hydrogen.
Yeah.
And if you have only metal on metal, you only flatten the very small roughness of the surface, and you can, if you have a high pressure, you can flatten these very these small roughnesses, and therefore you get a really good surfaces that you have a high tightness in these connections.
Okay, so but then you need to work really hard at making these surfaces really smooth.
So both parts should be really smooth.
Really smooth. Okay, cool. Right. So where do we see some of these things that you talked about? Where would you go and then?
We are talking also here about pipelines.
Pipelines. Yeah. Okay. Yeah.
I think pipelines are first necessary to transport the hydrogen, maybe from the coast. To all the towns,
so wherever it's needed,
to the plants and so on. And therefore at the moment we build very large pipelines. And there is a network for Europe to have the transportation lines through whole Europe.
Okay.
That's the one step. And the other thing is, if I have done the hydrogen at my place where I want to do something with the hydrogen, then I can use it maybe for any households, for burners, but I also can use it for electrolyzers. I can use it for gas engines. Here
so here we have so like
it's a large gas engine.
Okay. So those are the kind of areas where you have that applied. So now, Raf, we've understood the materials, we've understood the tightness. Now you're saying H2 ready. When, how do I now get the H2 ready stamp if I want it?
Yeah, if you want the H2-ready stamp, Jan, you have to come to us.
Yeah.
And to Dekra, and
that's how it looks.
And you, that's our stamp, yes. And you tell us what you want. Do you tell us?
I want the stamp.
Yeah, you want the stamp, but we are asking you, what's your leakage rate? Which material you want to use?
Yeah.
And so on. And we are doing a test plan for you.
Yeah.
We are discussing this test plan for you. And then we will do all the tests, and if your material, your component fulfill all the tests, then you will get the stamp.
Okay. So basically, I tell you what I want to do, and then you kind of make a test plan for me, and then you do the test, or I do the test?
We do the test for you. We do the test for you.
All right.
Because we have the abilities, the possibilities to do these tests also under hydrogen atmosphere.
All right. Okay. I think we have some. Yeah. This is. I looked through that. This is my favorite picture. Yeah. This looks like a dog bone, if I want to say. What on earth is this?
It's a small. It's a small vessel.
Yeah.
It's a pipe.
Pipe,
Here we have a pipe, and here the flanges. We can fill it up to 150 bars hydrogen, and inside we can put samples like tensile test samples, sharpie notch samples. But we can also here do some pipes from our customers who wants to age their materials.
Okay.
And but we have also larger chambers where we can put also complete components inside.
Okay.
And then either we fill the components with hydrogen, or we fill the outside, and so that the components are aged under hydrogen atmosphere.
Okay. So basically, this one would have been inside.
This one was there.
Well, this one was inside there.
Yeah, this one inside there.
So you basically you put it inside there. You push the hydrogen gas inside, and then you close it up and you write the date on.
Yeah, and then we wait maybe 50 days.
Okay.
What happened? And then we put them out.
Okay. And then you do the test.
Then we do the test, and we compare it with. We compare non-aged samples with aged samples, so that we can see, is there a difference? Is the material sensitive for hydrogen?
Yes.
And this can also be metals.
Yes.
It can also be polymers.
Yeah.
That's
okay. Yeah.
What?
Actually, yeah, because we have talked a lot about metals. To be quite honest. Yeah. And we use a lot. Yeah, but what about that? You know, like if I have my plastic pipe, can I come to you as well?
That's also it's no problem.
Yeah. Are there plastic pipes that are good for hydrogen?
Yes. When we
polymer. Polymer. Yeah. Sorry.
If you get in in lower pressure areas, then there are polymer tubes, pipes used for into the households.
Ah, yeah. So what kind of polymers are these? What kind of materials are these?
It's polyethylene, maybe polypropylene,
and they don't react with the hydrogen. They don't.
Normally there's no reaction.
I mean, because I know this really simple. I don't know. It's like sometimes you get a glass, a drinking container made of a polymer. If you drink out of it, you can taste that it has been in that polymer.
Yeah.
So I would assume that the polymers are rather happy to give us some of the.
It depends on the polymers. It depends various.
Okay, maybe we must look at that in a.
And I think you won't drink hydrogen.
No. Okay, cool. So here we see one of your tests set up.
Here
I think this is
one of the tests.
Yeah.
It's this.
This one we've already seen earlier.
What we see here. And the special of these tests is the samples here are drilled.
Ah, okay. So it's a pipe like.
During the test. This sample is filled with 100 bar hydrogen.
Right.
And the test is so-called slow strain rate test.
Yes.
And
so there is hydrogen flowing through there as you pull the pipe
during the test.
Wow. Okay, so that's a bit of a strain. Okay.
Yeah.
Okay.
And then you have.
And it's under pressure. The hydrogen.
It's
also.
under pressure. It's 100 bar.
100 bar. So that's pipeline running under 100, and somebody's pulling on the pipeline.
Yes,
that's what
this is these samples are made from welding sections.
Yes.
So that we can test the weld material and in comparison to the normal pipe material. If there is an embrittlement in the welding.
Oh, in the welding. Okay,
See, at the first, I think at the first or the second slide, we see that welding, that there are some embrittlements during the welding. And then we can see here there is an embrittlement, especially under hydrogen condition.
Okay, understood. One more test you have here.
Yes.
What is this one?
This is for the fracture mechanics tests. And here we put we first make the fracture mechanics, that's our sample.
Yeah.
We initiate first here a crack in this notch.
So this is drilled.
This is drilled.
Sort of drilled. Okay, okay. So this is a metal plate, and then you have here where you can connect your machine.
Yes, and then here we have the force.
Okay, so
we have a fatigue force. We have a fatigue. And here we'll start a crack.
All right.
And if the crack is started and has a special length, then we put the sample into a chamber. Well, it's also completely with under hydrogen.
Yes.
And then we do the test. We also have inside the chamber, we have the force. There's also fatigue force, and we will see how the crack runs then under hydrogen conditions in hydrogen atmosphere.
Okay. Wow, that's complicated. But why do you do this?
Because in a pipeline, you have hydrogen on a crack tip. Is very critical because high energy, the crack tip is an area where you have higher energy into a higher internal energy.
Okay.
And if you have higher energy, internal energy, then there is also the possibility that you get an embrittlement in the crack tip.
Okay.
And then you have a very the speed of the crack gets very fast.
Okay. And what kind of material would withstand that more? Like,
This is here we are at the moment. We test a lot of ferrite materials. Because these materials are used for the pipelines.
Okay.
But you can also use here a hardened material.
Yes.
But we may know these. Then we have the problem that hardened material. You see it before. It's critical.
Okay.
If there is a crack inside,
then
more critical.
More critical still. Okay. Wow. Okay, so you do all these tests, and you have your, let me say, thresholds until you
for the pipeline you has to fulfill a specialist threshold for these fracture mechanic tests. And if you fulfill this, then the material could be used for the pipelines.
Can you say a threshold? Whatever, is it like, I don't know, 15 Newton on the...
No, it's I think it's 55 megapascal. It's
there's a whole curve that follows. Okay, all right. Okay, well, I guess people have to talk to you. They want to know more about that. Thank you. I think we have seen this already, and also looking at the time. So that means those are the things that are needed. So you do material tests and you look at the leakage. Yeah,
that's right. And if you want the seal, we discuss with you and we decide what test would be necessary.
Yes.
You need not for everything all the tests.
Yes.
Maybe it's one test.
Okay.
Or maybe it's 4 to 5 tests.
All right. Okay. Different ones. Okay. Cool. So how long does that process take?
I think the process takes approximately 3 months.
Okay.
Because first we have to talk about what do you want. Then we have to machine the samples and so on, and then you get the seal, the report, and so on.
Okay. And then if there is aging, then
the aging problem is the thing. If you have 50 days to age something.
Is there a way of accelerating that? Can you make that more rapid?
No. Maybe you can rise the pressure.
Yeah.
It's also, but you won't. But in my opinion, you should age the sample in the same condition as it should be afterwards used.
Okay, so like wine, also you just have to have those days. Okay, cool. Ralph, to close this up, so where are we? Where do you see this going? You know, so we have the stamp that you made. Now you've explained some of the tests that go around there. Like how you see the future developments in this? You know, will your process get easier, faster, or you know, like will you be looking at other applications? Tell us a little bit of how the outlook is.
Yeah, the process I think for our understanding is that we has to if we want to save engineering, save under for hydrogen,
Yes.
then you has to make the tests to get that our customers will be sure that their applications was safe under hydrogen conditions. What we need for the future is more common standards, because at the moment our government says, okay, hydrogen, everything is hydrogen, but we see it takes, even if the government says high pressure from the time we have you have to develop something, and this is what takes time. And at the moment a lot of people are try to do some tests, but they use tests from former examinations, and they applicate it for hydrogen. And what we at the moment what we need is an common standards for hydrogen tests, so that we can compare the test results from one university to the other university, because they use different test methods, and they said, okay, our method is good, and we said, okay, this material is good for hydrogen, and the other said, no, it's not so good for hydrogen. Then therefore we have to use common tests. That's one of the most things what we have at the moment, what we need. And then we can also push up all the tests, because when we have a common test at the moment, we test the test whether it's whether we could use it for these components, for these material.
Okay. So more uniform standards will accelerate, which hopefully will accelerate everything. And obviously broader application, you know, will make all this faster. Ralph, this has been an absolute pleasure. Thank you very much for explaining, for taking us into the materials here. You know, honestly, material science is not always the easiest for everybody.
No.
I hope you have had some fun watching this. There's actually more videos on leak testing and so on that we have on this channel. Stick around a little bit, it can complement the picture. And Ralph, it's been great to have you. Thank you for watching. You can find people like Ralph on hyfindr.com to understand what there is that they offer in terms of all the certification, also components and so on that are certified. You can find on hyfindr.com, and look at our other channels as well. Thank you, Ralph, again.
Thank you.
And thank you for watching. Have a wonderful day.